I think it's time to kick this off then. Greetings, everyone. This is Stan Young with the National Renewable Energy Lab here to kick off and open up what we call our Infrastructure Perception and Control Workshop. Over the course of the next several minutes, we'll be speaking with you on both of our vision of how it's playing out. You'll hear from our collaborators, both with industry and with the city, as well as dive into some of the light details on some of the results that we've been having. First, as an introduction to myself, I work with the National Renewable Energy Lab as the Chief Engineer for Innovative Mobility. I'm also associated with the Eastern Transportation Coalition as their Chief Data Officer. So if you hear the term data, that's kind of where I work and live, whether it's data coming in from industry or data coming in from sensors. What we have prepared for you today should run pretty quickly. We want to get multiple perspectives and leave time for questions and answers. First, if you're not speaking, please be sure to mute out. I think that's appropriate. And let's see if I can get the slide deck going. I went over much of this. We'll be handing off quickly and giving you perspectives across the whole area of what we call infrastructure perception and control. And this is where I get to speak on the top level, the 50,000-foot view. I frequently start this way. AVs are the space race of our generation. I recently asked ChatGPT how much money did the U.S. spend putting people on the moon, and it answered $160 billion in 2025 dollars. And I asked them, well, how much have we spent on automated vehicles? And this was about a month ago, and it said about 80 billion. So we're in the same ballpark. There's vast amount of capital developing connected automated vehicles, but much of that technology is behind corporate firewalls. There's much less attention on advances in smart connected transportation infrastructure, what we call infrastructure perception and control. In comparison, there are approximately 300 signalized intersections in the US versus 300 million vehicles. So when you take a look at what can be done and what capacity, we think the signalized intersections, though we're not limited to signalized intersections, but the signalized intersections represent an opportunity. It's about where half of all crashes occur and excess fuel is expended. Smart infrastructure could save time, could save lives, could increase efficiency in the near term, and enable the next generation of what we call automated public mobility. But what is the challenge? The challenge, you'll hear open source framework many times. Let's not put this behind corporate firewalls. Let's get this out in the open. Let's create a framework for infrastructure intelligence that is scalable, sustainable, resilient, highly accurate, and probably the most difficult, affordable. Today, you'll hear addressed, here's some of the tech talk, the lack of a full state space awareness of all moving objects and communicating that effectively, and the lack of confidence and reliability of that state space model, more or less going from a single detector to multiple detectors with high confidence. We're seeking to develop a framework, an infrastructure perception control framework that is replicable to any infrastructure application to quantify levels of accuracy and confidence. We're going to fuse multiple sensor sources. We're going to develop open source mathematical framework for confidence, reliability, and self-calibration, validation, and health monitoring. Those last three are really critical to maintain the system long term. And we want to define open source normalized interfaces for 3D object tracks. There is a start towards that direction, and we're wanting to be in the corner that promotes that as much as possible. You'll see this chart again and again from NREL. It's the best chart we have of what we're working on. It flows left to right. This is our framework. On the left, we have our perception agents. Frequently, you hear LiDAR, radar, video processing. We also have real-time connected automated vehicles, as well as what we call CV data, which means similar data, but with more latency coming through the OEMs. These all come into our open source track data fusion algorithm that Rimple will be speaking to you later today, and then creating a 3D digital twin. This twin drives multiple applications on the right. Those are only 5. There are many more behind that. Once you get that confident 3D digital twin, it makes it much easier to create this whole framework and enable applications galore. So we're going from data to information to control. Some of these boxes represent the effort to do data standardization as much as possible, and that will be emphasized as well. The test. If this works, are you willing to use this digital twin? Ki Chow, who will be speaking later, has augmented reality glasses. Are you willing to either go blindfold or put on a digital reality that you don't get to see through your own eyes, but have to trust the data and have to trust it through these busy intersections? I've had a few colleagues that have been visually impaired throughout my whole life, and their ability to navigate on sensors other than their own sight always amazes me. So if you're brave enough, try to close your eyes and rely only on your ITS sensors to do this. This is the test of safety critical. I like to explain it in one way. There's an old saying, a man with one watch knows what time it is. A man with two watches isn't quite sure, meaning one watch tells you a story, gives you the mean time. Two watches gives you a mean time and a little bit of variance, how well you know it. As you build up your sensors, 3 watches, you can see whether they agree with one another, and if you have an outlier or a failure, you know which watch to send in for repair. You can carry this on a little bit longer than what we should, but as you build up the number of sensors, your idea of what ground truth increases, and your ability to tell the health of the system also increases. I'm stealing a little thunder from Fazan, who'll be speaking later. He came up with this: one sensor tells a story, multiple sensors tell the truth. I keep this in my slide deck mainly to reemphasize that what we're doing isn't necessarily new. The basic science behind this has been known mainly in the defense industry for years. I keep it up there mainly because of the little missile on the airplane saying this is basic science for anything in tracking objects in the DoD, and the mathematics behind it. What is challenging is bringing it to the terrestrial, bringing it at scale, have multiple sensors, and do it cost effectively. I keep this in my slide deck mainly to say there is no such thing as one great sensor. This shows LiDAR and radar. Of course, radar has the incredible advantage of range, and LiDAR has the advantage of incredibly accurate, close-in perception of vehicles and pedestrians. You need them both. There is no single best sensor. In this project, we've gone from concept to simulation to field demonstration. On the concept side, we've used tools like Carlos, Sumo, and Karma to simulate it all on the computer before we went to the field. On the left is the simulated input data from all the sensors, and on the right is the fused digital twin. And from that, we went to the field data collection in cooperation with our close partner, Colorado Springs. Thank you, Dan, and the city for providing all the support, the bucket trucks, the areas, and continually making it safe for us to collect data. And then this is where we're going to result and talk most of where we've been today. Collecting all this data, normalizing it, bringing it together in the same spatial frame, and then fusing it for a high quality digital twin. Going back to this framework, we'll all be speaking from this. I'm going to soon hand it over to Eric Ramat, who's going to be speaking towards this same basic framework, but from an industry point of view from his multiple decades. Then we'll hear from Dan. Then we'll start going into the various the technology realms, looking at our IPC laboratory, our data collection, and how it got standardized. And lastly, Rimple will follow up with the open source track data fusion engine. And that I just talked through. With this, I am going to hand it off now to Eric Ramat. Eric is probably known by most of you. He has had multiple decades of experience in the traffic industry, and most recently served for a year or two with the US DOT, and is going to come and bring us an industry perspective on this. So, Eric, are you available?
I certainly am. Thank you, Stan. Appreciate that. And if you could jump ahead a couple slides to my first meat and potatoes one, you can jump to the next one there. So I wanted to begin a little bit and kind of roll back the clock about 10 years. And those that were in the industry 10 years ago know that we put out this grand challenge of a smart city challenge. And we're really trying to focus on, let's pick one city and let's really put forward kind of this blueprint of what an integrated city is going to look like. And so a lot of cities came together and competed for this. Columbus was selected. There was $50 million of award as well as 90 million private sector investment put forward to this. So this was kind of, I don't want to say money's no object, but this was, let's put all our resources in to really kind of create a smart city and really blueprint out what the future will look like. One of the elements of this system was this Smart Columbus operating system. And this session is really going to talk about data. And, so there was $16 million allocated to putting together an open source framework for data exchange and kind of create this data fabric. The folks working on this were incredibly smart. They put together an incredible system. They really did a lot of great work within this program. But you can kind of see the tag at the bottom, this question about sustainability. Well, where is it going to be? And shortly after the program was done, the system was turned off and we kind of patted each other in the back and moved on. So that doesn't bode well for kind of how do we really get from where we are as an industry to where we need to go if $140 million can't create something sustainable within one city. And that was as of 10 years ago. And it had the right people, it had the right approach, it had a lot of the right elements. So something's really amiss. So before we kind of dig into the IPC, and Stan, you're probably going to the next slide. So what I wanted to kind of do was I wanted to touch on a sacred cow a little bit. This whole industry has marched to this drum of a systems engineering process, and all funded jobs kind of run this idea of let's develop a ConOps, let's make sure we understand the user needs and not build something that the users don't need, and let's run the systems engineering V process. So the whole worldview of how we spend money and how we deploy things really kind of has a program deployment focus. The operations and maintenance is kind of, we'll throw that over the fence afterwards and see if the cities can operate and maintain the equipment we deployed. And 9 out of 10 times, if there's a high bar of technology, agencies are just struggling, both with the technical resources and with the breadth of resources to really maintain this equipment. And so if you kind of look at the worldview of kind of a program-based deployment and the focus areas, we really focus on the systems engineering process rather than kind of the operational service levels needed thereafter. We always, are chasing this money, the capital expenditures and the grant money, but really what's the operational funding thereafter? A lot of products and a lot of product vendors really get into the APL QPL testing of a one-time validation that the product met the requirements as stated, rather than the real-time operational status of the infrastructure as it's working out there. People have a lot of focus on PICs and conformance to certain features, but really what are the real-time active capabilities of any system that's as deployed out there? So you can kind of look and say, well, if we put all of our focus into let's turn on a program, let's spend a bunch of money, let's kind of get to a certain state, and then we kind of relax the belt and go back to business as usual. We're not really building ourselves towards a real ecosystem of data. We're not really building ourselves towards a real maturation and maturity. And I don't think being good stewards to the taxpayer dollars and all of the efforts that go forward to this. So Stan, if you jump to the next slide, please. There we go. So to me, what's kind of missing in this is this notion of a service-oriented architecture. And when you do a program deployment and you give a big chunk of money to one vendor, that one vendor, it's going to be in their interest to deploy a monolithic system and to really try and have all of the things controlled within their architecture. And that is great as long as you're paying that one vendor service fees and that one vendor is incentivized to carry things forward. Really, another approach to this, and it's kind of a different mindset, is really thinking about the system as a much smaller broken set of smaller pieces where there's smaller services that each provide some level of service agreement, provide some piece to an overall system, and then what put together, there's a foundational architecture then that you can add more pieces to, you can extend pieces, and it's really kind of a modular approach to system architecture. It's vastly different when you look at the systems engineering V. There is a stage in there for architecture, but it very, very seldom really gets a strong focus in, hey, let's make sure this is architected for long-term scalability, maintainability, interoperability. All of those core tenets very seldom get put into an architectural focus. It's instead, hey, let's look at the use case and let's prove the use case and then we'll let the money flow. So if we really start to look at a service-oriented architecture and really look at that lens, what we realize is we have to look at the capability of some subsystem across time. A service is stood up, a service needs to have reliability, it needs to have accuracy, it needs to have a whole set of things that aren't a one-time, hey, we proved we did it, let's close down the project, but really it sets up for a time duration of how things should operate. Do we need 10 years out of this piece? Do we need 20? What are the agreements we need to make sure that these elements really run within that time frame and within the level of services offered? And if we break a big monolithic system up into smaller pieces, we can say, well, we need sensing. We need something that's going to fuse that and create a geospatial model. We're going to need certain applications that then use that data. So all of these pieces and parts, if looked at from a lens of a services architecture, you still get modularity and interoperability, but you also get scalability and growth. So ideally, when we're looking at this IPC in the next couple hours, I'd love you to look at it from really a service-oriented architecture lens. And I think that's the foundational shift that the industry needs to make as we move forward. Next slide, please, Stan. So when we talk about detection and situational awareness, the current state of standardization and state of practice is really all of these smart sensors emulating loop detectors and placing loop presence inputs and then falling back on traditional control systems that have been in place for 40 or 50 years. We've got a state of modern technology where we can see red light runners running the red light before they get there, but the control equipment and everything else that's per standard really doesn't have an ability to do anything with that advanced data. So what we're trying to do is really close this gap between the current state of standardization and the current state of modern technology. Now, the pace of standardization probably isn't going to get us there fast enough. Standards move in the order of decades. This technology moves in the order of months. And so we have to really be able to close that gap down if we want to get to a framework where we can take advanced technology and deploy it at scale within the industry. Next slide, please, Stan. So we're right on the cusp of now releasing the next standard for connected vehicles and autonomous vehicles in the SAE 3224. This is where we're going to start to share sensor data or perception of the roadside with vehicles, and vehicles are going to share that with one another. And so this now, when we're looking at this I think is going to really unlock a lot of the safety issues and really give a broader, transparent fabric of what do we see geospatially going on in the intersection, and how do we share our information with the other agents, and how do we collectively make things safer, make things more efficient. Now, if you're looking at this message, we had 20 years of fits and starts trying to get just basic signal phase and timing data from an intersection to roadway users. And now we're talking about sharing sensor data. So there's a clear need for us to move towards real operational, services based. How are these things performing? Is somebody validating that the sensor is accurate? Is somebody validating that the data is characterized? And we have to be able to manage this as a living system, especially if vehicles are expected to ingest and consume that and make left turn driver assist and make other safety maneuvers based upon this data. So the stakes are really raising here. And the fact that the 3224 is now being put forth, we really need to make sure the infrastructure isn't just running good enough for the signal not being in flash, but is really preparing and publishing data that is consumable and trustable. Next slide, please, Stan. So when we look at our standards, and I'm not trying to bash on standards, standards were largely developed starting in the 1990s around SNMP and around human readability of the data sets. We've built a whole ecosystem of products that conform to the NTCIP and the other standards, but those standards were not designed thinking, hey, the data within these and how these is encoded, this is going to be put into a real-time safety system where the vehicles are communicating with the infrastructure. People weren't thinking those use cases. People weren't preparing for that. We were just trying to get basic vendor interoperability between ATMS systems and field devices. And so now we've got decades of deploying these standards. We've got $50 billion of as-built infrastructure that we can't throw that baby out with the bathwater, but we've got to be able to take what we've got out there, adapt these data systems, and be able to publish trustable information for AVs and other roadway users. We've got 40,000 fatalities a year on our roadways, really, I think, dependent upon us solving this problem. So much of the modern technology can prevent these deaths, but we've got to get this 50 billion as-built infrastructure modernized and at least bolting into more progressive means of carrying this forward. Next slide, Stan. So when you look at this problem statement, and I hate to bash on Columbus because they really, I think, we're tried to do everything right. And yet today that whole industry focus and spend really didn't create anything. So when you kind of unpack that, what you realize is a lot of these challenges are big. We've got funding challenges. We've got to get away from a big lump sum of asset procurement money up front and not operational budgets. We've got to load level that. So we're really focusing things more operationally. How do we channel that money to be operational funds that can set up for services architectures? We've got a political hurdle to overcome. Mayors and other folks love to have a ribbon cutting and say, hey, look what I accomplished within, my time on the watch, rather than what is the operational state of this system, and I'm going to take accountability for it. Ribbon cutting provides a really, really clean political win, but it's not grounded in the reality of really moving this industry forward. As well, we've got a lot of consultants that love to copy-paste ConOps, copy-paste requirements, and really just churn the engine of what we've been doing for the last 3 or 4 decades and make money doing so. And I'd be curious to see on the Columbus money, how much money went into consultants' hands versus how much really went into infrastructure products. I think there's a big problem there with the consultancy and how we're kind of doing that rinse repeat, money machine within that. As well, there's a lot of technical work areas we got to work on. We've got to convert, upfront specs of, hey, let's test the product one specs to really a service agreement of how does this product work within an ecosystem and how do we put a framework of accountability around each of the products. We've got to unpack data trust if we're publishing data like 3224 to vehicles. There's a whole element of trust that goes very, very deep in how do you get to published data that is secure, that is reliable, that is characterized, that is validated. And to me, ultimately, what I think we need to do is move towards a unified service-oriented architectural framework that is going to be technology neutral, that is going to allow these pieces to all come together and interoperate, and is going to provide those key trust layers. I see the IPC as one of the foundational pieces of this, especially around the 3224 message, and especially around getting a situational awareness of what's going on within the intersection published out there for the broader applications and use cases. So with that, I think I spent a little bit more than my 10 minutes, Stan, but that's what I wanted to cover. Next in line here, I'd like to hand the microphone over to Dan Sines. Dan and I began working together probably 25 years ago. He, in fact, was my first boss in this industry. And Dan has spent the last 2 decades working with the city of Colorado Springs, trying to deploy trajectory-aware control systems. And he did get some initial funding and is still continuing to look for additional funding to scale this across the city of Colorado Springs. And as somebody who lives local to that area, I love this idea of really promoting that next generation of safety with trajectory awareness in the control systems. So with that, I'll hand it over to Dan, and Dan, you can take it away from here. Thank you.
Thank you, Eric. I appreciate it. So I want to focus on how the signals are controlled, the intersection, how the lights are controlled by the intersection controller. So let's take a step back and think about what does the controller perceive as it decides what signals to illuminate, red, yellow, green. So traditionally, all of the controllers are ingesting detection data. And detection data is basically point data. In other words, it's like looking through a window and seeing only a snippet of the traffic. So when someone pulls forward into a left turn bay and they're waiting to get that left turn arrow, all the controller gets is one bit of information. Something is present. One or more vehicles are present, waiting to get that left turn arrow. Or if a pedestrian pushes a button to get that crosswalk signal, all the controller is getting is one bit of information. Someone is waiting to cross in that crosswalk and needs that walk signal. So it's just basically a small window of perception into what's going on in that intersection. So what we want to do, what we've been talking about, is let's pull that whole wall away. Let's eliminate that wall. Let's eliminate the need for a window. Let's give ourselves a complete perception of everything going on in that intersection. A three-dimensional, real-time digital twin of all the objects approaching within and exiting that intersection. So let's track all the vehicles, all the pedestrians, all the cyclists. Let's build a 3D model that is real time and then feed it into the controller. With that level of awareness, with that level of perception, what can the controller do? How much more intelligent can the controller be when it manages the flow of traffic through that intersection? We can make incredible efficiencies improvements. We can make incredible safety improvements. So there's detection, what the controllers are ingesting now, which is just basically single point, one bit, something's there, as opposed to a whole data set about an object, a three-dimensional location, a vector of travel, and a classification. What is it? Car, pedestrian, truck? So that's the difference. We want to go from detection to perception with the infrastructure perception. So next slide, please. So a little bit of background of where City of Colorado Springs has been. So back in 2005, the City of Colorado Springs made a bold decision to develop their own intersection controller and their own firmware. And the reason was the city really was struggling to see how the industry was going to coalesce around a single platform. The traditional platform was fading out. It was based on some raging 70s technology, and it was becoming unavailable for replacement and building of new intersections. And the industry was struggling to focus onto a single replacement platform. So the city said, why don't we build our own? Why don't we start out and build our own intersection controller and develop our own firmware? And that decision gave us a real golden opportunity. And with that opportunity, we then partnered with a company called Wavetronics. And Wavetronics provides what they call advanced sensors. It's a radar device that has a one-dimensional perception, but it tracks all the objects approaching that from that one direction. So with 4 sensors, we can see in all 4 directions, and it's the speed and distance of each vehicle as they approach the intersection. And instead of just providing the intersection controller with a bit of information, we now are providing the controller with speed and distance of each approaching vehicle. And that's where we started back in 2016. So 4 sensors, 4 approaches, real-time perception of all the vehicles that are approaching that intersection. So in 2016, like I said, we started working with Iowa State University, and we came up with the first trajectory-based control for an intersection. So the intersection was allowed to, based on that real-time data set, make its own decisions about when is the safest and when is the most efficient time to go from green to yellow, to start ending that approach. And the things that it was basing those decisions on are, if I've got a platoon, a movement of vehicles, a cluster of vehicles approaching the intersection, let's try to keep them moving. Let's not break them up. Let's keep those platoons going until there is a bidirectional break in traffic. Once there's a break in traffic, then that's the perfect opportunity to service the other direction, or the pedestrians, or the left turners that are waiting to get through. Secondarily, we were looking to eliminate the dilemma zone. So if we can see the vehicles in real time, and we know as the dilemma zone is as you approach an intersection, when it goes from green to yellow, you think about, should I hit the gas or should I hit the brakes? Can we eliminate that dilemma? Can we make sure that none of the vehicles are in that 3 to 5 second period where you question what you should do? So let's try and clear the dilemma zone. Let's try not to break up platoons. Let's find the most efficient time to turn from green to yellow. And we successfully deployed that in 2016, and it's been running ever since. Next slide, please. That set us up for nearly a decade later, a partnership with NREL, University of North Carolina at Charlotte, University of Alabama, and a continued partnership with Iowa State University. How do we go from this first generation system, that first generation system where it's only seeing one-dimensional data in each direction? How do we build a full 3-dimensional digital twin that represents all of the movements, everything that's going on in the intersection, and build it in real time? And this is where, as a team, we pursued a SMART grant so that we could go from this first generation system to the next generation, and not just contain it within the city of Colorado Springs, but let's build, like Eric said, let's build something that can expand nationwide, that can be a basis for nationwide interoperability, providing a digital twin that's not just for intersection control, but so many other applications. So once we have in that level of perception, that data set being provided to the intersection, we have a lot of opportunities to increase safety and even further improve the efficiency of the operation of that intersection. We can see approaching emergency vehicles, first responders, and the vehicles that are in between them and the intersection. How should we manage clearance of that intersection? We can see red light runners and definitively know that they're going to run the red light. How do we mitigate that? We can take care of those individuals who are mobility impaired, and do they need extra time? Can we track them and hold off the rest of traffic to get those mobility impaired pedestrians out of the roadway? And then let's work on some more efficient operations, intersection to intersection. Do the intersections self-organize? And ISU has shown that yes, the intersection can self-organize based on this data set. We can minimize delay. And when we reach full congestion, when we reach that rush hour period, let's balance the pain. Let's make sure that not one direction gets stacked up too deep. We can perceive the depth of the queues on all four approaches, and let's balance that pain out so that we can make things more efficient for everybody instead of a select few. Stan?
Thank you, Dan. We are going to continue with this. Our first three speakers, myself, Eric, and Dan. How do I put this politely? You're hearing from people that are closer to the end of their career than their beginning. We're looking at where we need to go, where we've been, and saying this is how we need to get there. The next three speakers, conversely, probably closer to the beginning of their career than the end, are the technical specialists that are going to come on and show you some progress towards this IPC infrastructure, each from a different perspective. With that, I'm going to stop sharing and invite Qichao Wang. Qichao, if you want to bring up your slides, and I'll provide an introduction. Qichao is from the National Renewable Energy Lab. He's a computational transportation scientist. You don't hear those three words very often at NREL's Computational Science Center. He holds a PhD in civil engineering from Virginia Tech. His work at NREL bridges advanced computing and transportation systems, including high-performance modeling, simulation, optimization, control, and visualization of mobility systems. He co-started the NREL IPC Lab and continues to help move it forward. He led the development of the open source NEMA controller using InSumo, which enabled about $25 million in research projects, including energy interests, DOT interests, and state interests. He is the NREL PI for the ARPA-E NextCar project using high-performance computing and augmented reality to test connected and automated vehicles. With that, Qichao, why don't you take the con and take us through this next section, looking at the infrastructure perception and control lab capabilities.
Sure. Good morning, everyone. First check, do you guys hear me?
Yes.
Okay, good. We found in the past work that the real world behaves quite differently from the simulation. And the technology that we develop in the simulation and perfected may not even work in the real world. And we need a lab to help us bridge from the simulation and the real world together to help accelerate the iterations of the technology improvement before we wait until the last minute to see it. Basically, when we start the research, we want to work towards a real world application. That's what work in a real world system. With that, we started the infrastructure perception and control lab about 2 years ago. Being a DOE lab, energy is usually where we started, and being transportation industry for a while, we also understand that we also need to look into the efficiency and safety. So that's the overall purpose of this lab. With this lab, we develop capabilities in sensor perception, data acquisition, high performance system modeling and simulation, optimization, command execution through NDCIP. We also partner with City of Colorado Springs to roll out a full pilot implementation. And this lab basically provides a capability that finishes the full cycle of the capabilities to affect the real world, from sensor data from the real world, understand the information from the sensor data, and understand the system with the domain knowledge, modeling and simulation, to optimization and decision-making until it accelerates the actions into the real world that will affect the data sensed by those sensors and continue this loop forward. This lab includes 3 tiers. The tier 1 is the traditional building lab space with about 450 square foot, including bench space, workstation, wall mount, monitors for real-time data feed and visualization. So we basically prototype things here and do from modeling simulation to some prototyping on the hardware before we move on to the next tier. That's the track testing. This track is conveniently just by NREL on top of the Mesa. It's owned and operated by Colorado State Patrol Academy, and NREL has an agreement with them to use the track when they are not using it for training, and we can use it for research purpose. It's about 1.4 mile, good enough for many usage. And after we test things well and think we are ready, then we move on to field deployments through our partners, including City of Lakewood, Colorado Springs, etc. And all the technology that we develop here will be modularized, meaning we can just take the thing from the lab space, wrap it up, and move to the track, and still wrap it up and move to the field. And the trailer that we put together is the vehicle that's carry us from one tier to the next tier to the next tier. So everything will be modularized. If it work here, it will work there. That's the idea. And I mentioned we started the lab about 2 years ago. It's beginning of 2023. By mid of that year, it's still empty room, but behind the scene, we are very busy doing the acquisition, talking with vendors, industry partners to help configure this lab together. And then we come up with this design. Basically on the left side, we have the conference space. It's include a large screen with 3 mid-side display and a conference table with whiteboard for brainstorming. And on the right side, you see a traffic cabinet with a computer desk and the bench with all sort of devices, sensors, controllers, mixed reality devices, and so on. And by the end of that year, we start putting things together. The device start arriving. You will notice that we also have a 3D printer to help us prototyping all those devices that were put outside in the field. And by next year, we start having all those devices up. You'll see this gaming steering wheel is not really for gaming, it's for a virtual reality, more of an immersive environment for driver to start the human behavior of it. And then the track, this is a nice photo taken from a drone. It's very beautiful. We went up there and saw really good view there. And it's very convenient, very next to NREL. You see the solar farm here, that's NREL campus. And not too far away, that's just the track. And also, we work closely with Colorado Springs. They operate over 600 intersections. And when we configure the lab, we have the exact same traffic cabinet and associated devices to make sure everything we develop in the lab can be seamlessly transitioned into the field deployment in Colorado Springs. And we also work together on that SMART grant together from USDOT. And then I mentioned the trailer. It's a very important piece to help us move from the NREL campus to the track to Colorado Springs or Lakewood, City of Lakewood, and make sure that everything that we do here would work outside. And we understand, like many times we just imagine it pretty well inside of the house and find, oh, it may work. We write a code and hopefully everything works. But in the reality, when we get there, it may not work. And many times we were in last minute light development. So this trailer helped us to do that. It's weather controlled. Colorado can be quite a lot in terms of weather, and include all those devices. We have nice design to hold all these devices. Those are some photos that we took when we are operating outside. The mast go about, like, I guess 20 to 30. Well, this one is like more like 20 feet tall. And include all sorts of sensors, LiDAR, radar, camera, or sorts with other devices connect inside of this trailer. And you see files on here, configure those devices, and sometimes need to do the last minute development and tweaking, debugging. We also able to connect with the local infrastructure to the signal cabinet to get the sensor information from the local sensors. And it's not just a lab of devices, hardware and expertise in transportation, but also with the support from computational science, including the modeling and simulation, AI optimization, data infrastructure, and visualization, supported by the ESIF high-performance computing and data streaming and visualization capabilities. And this is the architecture that I imagined, how this three-tier lab connected and work both in the real world and the virtual world. It has three tiers, including indoor, track, and public road. Within each, we have the onboard device and the roadside sensors. And on the right side, that's the simulated world on high-performance computing. Everything simulated with our modeling and simulation capability. And in between, we have the real-world data infrastructure connecting the information from the real world to the simulated world. And I understand there's a big factor in the mobility system that is a human factor. So we have been developing this mixed reality human interface to bridge between the real world and the simulated world, so that we can test different scenarios and without exposing the human into a dangerous environment. And the idea of this three-tier is basically start from prototyping, closer to theoretical work, to a more of a protected environment testing. And after that, we feel comfortable enough, then we can move into the public road where we expose the new technology in the real world environment. And this is the work I want to mention that was just done about 2 weeks ago, the track testing connected autonomous vehicle with augmented reality. It's a bit crowded here, but let me walk you through. On this top left side, that's basically from the national representative drive cycle. We have about like 40 million drive cycles collected through all the past projects throughout the years. And use that, we inform and calibrate the way how the driver will drive in a simulator called VTD, Virtual Test Drive. And use that to interact with the real world vehicle on the test track. Basically, the real vehicle has onboard unit, talks through the roadside unit, sending the basic safety message through V2X communication to the simulation server. Simulation server does the vehicle in the loop simulation and basically fix those PSM from the simulated vehicle and sent through the roadside unit received by the connected vehicle, so that the connected vehicle can drive accordingly. And on the lower side, there's a big part that's the observation deck. It looks just like this. It's basically a container. And in it, we have the portable RSU receive all those PSMs on the air and send through the wireless router route to BSM/visualization server. It decodes the basic safety message and forward to the visualization server that does all those 3D visualization and localization of the real world. and send through the Wi-Fi wirelessly to the AR goggle. And then observer can see how things will go. They can basically see how the vehicle running on the track together with the understanding of those vehicles together with the simulated vehicle and communicate with the simulation server to confirm what they see are aligned with what they intend to be tested. And after all this tests, it's for move to scale up the impact, basically using the national representative drive cycle to see, after we test it, we see how the autonomous car will behave. We embed those behavior into our model and scale up the analysis to a nationwide, see how much impact would be nationwide if all the cars drive like this cars. And this is a snapshot I took during the test. Basically, you see the real car here through a window. It's kind of interesting that Dan just mentioned the difference between the sensing and perception. One is looking through the window, another is walking around and see how the real world look like. And with augmented reality, you can actually see through a wall. Although through a window, you can actually see through a wall. All the cars around is actually give you a nice visualization of what's going on out there to inform your decision making. You were imagining augmented reality may just be a nice piece to add to help you see things, but seeing is quite an important factor in testing a complex system. And when you just look at a chart, look at the numbers, you're kind of expecting what could go wrong and see if something did go wrong in that direction that you're expecting. But when you immerse yourself in that environment, it can actually help you to identify what went wrong or what went right. And here's the video I took when we did the test during, well, I guess that was back in April. You will see this car. Why is this car like so far off and looks smaller? It's like about 30 meters under the ground. And when I ask people and they say, oh, we just realized that there's a difference on the understanding of the shape of the Earth, basically where the elevation of 0 is at. From the simulation, they basically had a very nice map of the track. It's referenced to a sea level. A sea are at different level, different part of the world. And the GPS basically have a model of the Earth and imagine the Earth look like this and that. So they have a difference in the understanding of where the level 0 is at. And that difference at that side is about 30 meters. You won't really see that until you see this. If you just look at the animation from the simulation, you will think, oh yeah, X and Y look great. But when you test it with the real vehicle, the vehicle will say, oh, there's a car about like 30 meters up there, and I don't really care since it's not really on my level. I'm not gonna crash into it. So that shows some significance of this technology, and we think this technology can have more impact in the future as we keep building up our capability at the IPC lab. Well, with that, I'm going to introduce Faizan. Faizan Mir is a researcher at the Center for Integrated Mobility Sciences at National Renewable Energy Lab. Mr. Faizan Mir's technical specialty include robotics, sensor perception, control systems, and data fusion. As part of NREL Infrastructure Perception and Control Lab, Mr. Mir has integrated multiple sensor modalities in the IPC mobile lab, a key platform for the sensor testing and data collection under the US DOT SMART grant in Colorado Springs. Faizan?
Yes. Are you able to see my screen?
Yep.
Okay. Yeah. Thanks, Kijao, for the introduction. I'll dive deep into a little bit of the data collection methods we employed for the IPC. I like to bring up this slide because it gives a good visual of like how the different sensor range affects like how detection capabilities at the traffic intersection where you have like this radar giving a long range detection, telling the controller what vehicle's approaching, and this LiDAR detection, which has a smaller range but gives a more dense point cloud telling us like what actually is going on in the intersection with high accuracy. And the key here is like to evaluate some of these sensors and then maybe potentially fuse these together. As part of the project, we basically focused on 3 sensor modes: camera, radar, and LiDAR, which are the most common sensing technologies out there. Of course, there are some like additional sensors like thermal cameras, but our focus has been mostly on these, which kind of we will do in this talk. All the sensors have their own pros and cons with respect to how they operate, their range, and how they perceive the objects in the field of view. With camera, we get strong object detection, can identify different types of cars, buses, and pedestrians, but has lower range. And then really the detection and tracking capability depend on the kind of tracking algorithm or deep learning algorithm we use. Radar, on the other hand, has superior detection range, which we have found it is pretty robust in different environmental conditions, but the detection of VRUs is not that great as compared to some of the other sensors. LiDAR, on the other hand, has a pretty good detection, object detection and classification, but has limited range and is affected by some of the inclement weather conditions. I'll dive into some of the data collection methods. So as part of the IPC Smart US DOT Smart Grant project with the city of Colorado Springs, we were able to like collect data from multiple traffic intersections and get a mix of sensors deployed at traffic poles and on the IPC mobile lab and also have a different road environments such as high-speed intersections, urban and rural environments and road sections to kind of challenge and gather data from multiple sources, multi-sensors, and multiple environments. Here, I'll present some of the results from one of the test intersection, which was done in October 30th last year in the city of Colorado Springs. At NREL, I wanted to point out the IPC mobile lab trailer that we have here. We were able to use this IPC trailer to deploy some of these sensing technologies. On the left, you should see some of the radar, LiDAR, and camera sensors deployed on each of these masts. And this mast goes up to 30 feet. So this helps us to like quickly head out to a road intersection, deploy some of these sensors, and then collect the data, which kind of has the same field of view as you would have if it was installed on a traffic pole. And then inside is mostly like edge compute and all the data collection equipment where all the sensor data comes in and then it gets like processed and fused over there. Talking about the test intersection, one of the intersections that we did the test at the Colorado Springs, it was a mostly high-speed intersection. So we also had 2 pole-mounted EVO radars from Colorado Springs, and then we placed our IPC mobile lab over here at this section to capture some of this data. Additionally, the traffic cabinet was located over here, so we were able to connect some of the data from the Colorado Springs, the radars, from the traffic cabinet into our IPC mobile lab to get like detection from all the 4 radar sensors at the same time. Additionally, we also employed a high accuracy GPS, which consists of like a base unit set up at the test site and also a rover unit set up on a test vehicle, which drove around the intersection while we were collecting data to get us some of this ground truth so we can validate and calibrate some of our sensor data that we had coming in from these perception sensors. This slide presents a little bit more information about how the field of view of each sensor is. So the top left image shows 2 radars placed diagonally opposite to each other, providing a full intersection coverage. We're able to get all 4 approaches and some overlap within the field, within the intersection. And on the second image shows the sensors deployed on the IPC mobile lab. The image on the below shows the sensor schematic, how each sensor was data was collected, sent it to edge compute, and then also from the Colorado Springs side where we have 2 radars connected to an EVO hub, and then sending the data to the edge compute inside the mobile lab. In order to like time align this all of these sensors because they're distributed across various edge devices, we employed an NTP server which pulled data and then synchronized all of our sensor data using this. The table on the right gives some specifications of the sensors. We had multiple Evo radar units, we had ouster sensors, we had Septon lidars, and we had an access camera deployed as well. One of the key characteristics of any multi-sensor fusion is like spatial transformation, which is the first step where we have all the sensor data coming in and we need to like align it to a common coordinate frame. Basically, we are doing 3D Cartesian transformations to bring all the point cloud data together into the same coordinate frame so that it can be further fused. One of the key challenges we have in the sensor calibration is aligning actually some of these sensors together, which is currently it's mostly manual and then is very sensor agnostic and highly dependent on a calibration object placed in the field of view of all of these sensors. So we can find the transformations between each of them. So our goal has been to create a highly accurate multimodal sensor calibration approach for infrastructure-based sensors, so we can align all of these together without the need for a calibration object or having to do it manually. One of our papers explores how to use connected vehicle data to calibrate our infrastructure-based sensors. On the left, you have the first image showing the the vehicle tracks of the GPS that was driving along the intersection. And then we have, as it drives through the intersection, it gets picked up by different sensors. In this image, we have 2 radars picking up the object. And as they drive along, you can see the vehicle tracks. And these are not aligned with each other. And we use the GPS vehicle tracks to basically set up an optimization problem and bring all of these together into a same coordinate frame so we can send it for data fusion. These are the outputs we have from our infrastructure-based sensors we deployed at the test intersection. So we have 4 radars, 2 lidars, and a camera, all the data coming into their local coordinate frame. If you look at the radar data, it kind of looks like they're all looking at the same direction, but yeah, I showed it in my configuration slide where every sensor was looking at a different approach. So basically, we have to do coordinate transformation and calibrate some of these sensors to bring it into the same coordinate frame. Once we do the transformation, we're able to see this image, which shows not the fused object list, but all of the sensors overlaid at each other, providing an image how different sensors range is and how we can use some of these sensors overlaid on each other and fused together to create a more robust and reliable image of the intersection. I want to go into a little bit about the sensor evaluation. So the slide here shows like the object track from the LiDAR. So a lot of the sensors use some kind of prediction algorithms to keep a consistent object ID to account for like occlusion. So as the object goes behind a tree or any other occlusion and comes out on the other side, it keeps that same object ID. And the issue with the sensor is, as we move out of the field of view of the sensors, we start seeing some of these vehicle traces being predicted, which are not very accurate. As you can see, some of the streaks of those tracks coming in. So if you notice, if a vehicle's turning right, a lot of times the LiDAR predicts that it keeps on going right, which is not correct. And it also helps with the LiDAR to keep increase their range. So in the sensor evaluation, we try to work only with LiDAR detections and want the IPC fusion engine to hold all the predictions that we have multiple sensor data coming in so we can make more accurate predictions. This slide shows the sensor range where you can see we have 1 and 2 on the traffic poles with the radar almost seeing closer to 450 meters from the intersection. There was a pretty big intersection with a pretty good field of view and a line of sight as well. So we were able to see pretty far ahead. And on the right, we have 2 images from the 2 LiDARs showing like how the difference in the range is, where we have LiDAR able to see only about 100 meters. And this was a pretty sunny day. So depending on the placement of these sensors, we might see reduced range from some of these sensors. Just to summarize what we covered here, camera detection really depends on like what kind of object detection algorithm we use. There's issues with if we set up a multi-lidar setup, the calibration is an issue as we manually need to align the point clouds together. Cost is also a big issue when using these sensing technologies, and also long-term reliability as well. Bringing back the same slide, so there's no best sensor we can apply for all of these environments. We have to use a multimodal sensor fusion approach to combine all of these sensors and then to get a more robust image of the intersection. Here we can see like if we overlap some of these key characteristics from the sensors, we can basically get a better and robust image from all of these sensors. So we can have the radar camera fusion and radar lidar fusion. And if we have all of these sensing technologies, we can basically get a much more robust, a rich image of all the objects moving within the intersection, which Rimple will be talking a lot more about in his IPC fusion engine approach. I want to go quickly into sensor analytics, where we found out when we were deploying some of these sensing technologies that each sensor brand comes with its own analytics package, its own perception software, which is hard to navigate if we have a lot more sensing technologies, different modes of sensors. And by looking at some of these, we're not able to basically get the key metrics out of it. So we can look at the vehicle tracks coming in from the LiDAR or the radar, but it doesn't tell us much about how the sensor is performing, how the data is coming in. So having a data quality metric is pretty important for a traffic controller figure, where we can specifically tell that we want this kind of data, and then this should be the quality of data from each of these sensors. And then it is pretty difficult to navigate across multiple interfaces and increases our cognitive load as we try to implement these sensors. So this is where we try to work on a IPC smart dashboard, basically a data analytics dashboard, which takes in data from all of these sensing technologies. This is kind of works on the same theme as being sensor agnostic. So as long as the data is coming into a specific data format, we're able to visualize it without having to like switch screens, switch softwares. And then it also, in addition to giving us object counts and the intersection map, we can also we're also able to see some of the key data metrics from the sensor, which tell us about how the data health is, how the sensor is performing, and some key characteristics about these sensing technologies. This is my key takeaway slide, which kind of summarizes some of the previous slides. So we really need a sensor fusion, as we cannot get a robust perception from just using one sensor mode. Spatial and temporal synchronization is very important if we have if the data is not calibrated correctly, or it has errors in time and the spatial coordinates. Fusion really struggles in those environments, and having a GPS timestamp across the sensors really helps, as the reliable data connection is not really available at a lot of traffic intersections. Standardization is very important, as well as we have multiple sensing technologies from different brands and vendors. We want to have a common data standard where it sends the data in a single format, and we're able to fuse it into the Fusion engine. So this also helps with the cities that they can as it also helps with the cities, as it helps with them with the vendor lock-in as well. So they're not confined to one single vendor, and we can also integrate some of the newer technologies that are over there into the same Fusion engine as we go along. A smart dashboard, which I explained, really helps with the multimodal sensor data visualization, and helps give us information about how the sensors are working, and then what is going in the intersection, without having us to like dig deep into the actual data. I'll repeat one of the quotes. One sensor tells us a story, many tell us the truth, where we only have one sensor giving us data, but if you have multiple sensors, we know what is actually going on, and we can compare the data from some of these sensors. I'll conclude with this final slide. this is the IPC multi-sensor object tracking data set that we published as part of the smart grant with Colorado Springs. This is one of the few multi-sensor infrastructure side data set that is out there from traffic intersections with having these many sensing technologies collect data at the same time, and also be tested it out at different intersections and different layouts to kind of get like a full perspective. Yes, thank you.
Thank you, Fazan. Thank you, Ki Chow. Thank you, everyone. We have one speaker left bringing this all home. I hope you've gotten the sense. We gave you the overview. We laid the groundwork as far as getting data in. Now this all has to be processed into one comprehensive view of what's actually going on there, the truth, the ground truth, so to speak, or how well we know it. Next, Rimple Sandhu from NREL is going to come on board. Rimple is a computational science in the Computational Science Center at NREL. He's an expert at scientific machine learning and data assimilation, particularly with Bayesian filter and high performance computing. A lot of big words there. These are the same disciplines that go into data fusion and brings out the best picture of what's actually going on the road. He has been leading the IPC effort on multi-sensor data fusion, and we'll be talking about that next. Bring us home, Rimple.
Thanks, Stan. Can you see my screen and hear me properly?
Yes, on both accounts.
Perfect. Thank you, everyone, for joining here today. This is a very important topic, and I'm going to share the multi-sensor data fusion aspect of this work. Start off with the introduction, what multi-sensor data fusion is. Then I will quickly jump into results with simulated data from Carla and Sumo, and then go into field data in a controlled setting and uncontrolled setting, and then conclude. So let's bring that same figure from before. So multi-sensor fusion comes in when you have track level information from different perception agents. I would like to stress here that we are fusing tracks, meaning late stage fusion. We're not in the business of early stage fusion, which is also refers to as point cloud fusion, which is most of the work on the vehicle side is on fusing point cloud data from different sensors. We're assuming that this perception agents that we have in an intersection, they have their inbuilt machine learning module that processes the point cloud data, produces a track, and then that feeds into the fusion engine that we have built. So this goes back to what Eric mentioned is, can you have this situation where you have sensors from multiple OEMs, they have their own service agreement, they have their own machine learning module that process the point cloud data to a track. We don't know anything about what goes on under the hood, but can we take the information that they give us and then fuse it to produce a digital twin that can then feed the control applications? So what is the goal here? We want to build a fusion engine that fuses information from multiple sources about roadway occupants, pedestrians, vehicles. And we want to do that while making it sensor agnostic, meaning it should work for radar, LiDAR, camera, V2X, different sources. OEM agnostic, if you get radar from one vendor and then you try to switch it to another vendor, it should still work, should be OEM agnostic. Scalable, it should work if you have 10 vehicles or 100 vehicles or 200 vehicles, it should work in different situations. Real time, we should have it run in real time. And this goes back to the scalable component. This needs to be running on edge hardware, which is typically compute constrained. So you need to make sure you design this algorithm to run it in a compute constrained hardware. Resilient, if one of the sensors goes off, it should still work. Object type agnostic, it should work similar performance for vehicles or pedestrians. It should not discriminate between if it's a vehicle or a truck or a pedestrian, different performance. So we want to make sure that connected. Once we have this digital twin, can we send out this information to cars who want to use that and augment that with their own inbuilt perception software? So we want to make sure that we have this connected aspect as well. So we want to cover all these aspects when we design this. And what is the challenge? Biggest challenge is each sensor lives in its own world. Okay, one sensor will give you position information. One sensor will give you velocity and acceleration. The other sensor will give you 3D shape information, length, width, height. Other will not. So you have different information coming from different sensors, and they have different spatial resolution, radar versus LiDAR. You have different range. You have time resolution. One sensor will give you data at 2 hertz, the other will give you at 5 hertz, the other will give you at 20 hertz. So you want to balance that and figure out how to deal with that. Range of detection, reliability. Some of the sensors, they have different performance when the vehicle is further away versus close to the sensor. Confidence levels, sensors, they vary on how uncertainty is computed and how it's provided to the end user. Calibration setting, it's as Faison talked about, each sensor comes with their own calibration settings, and it's sometimes there's issues, so you want to make sure that you are taking that into account. So there's different heterogeneities in these sensors, and when we build this fusion engine, we want to respect these and make sure we account for these in one way or the other. Okay, so what is multi-sensor data fusion? As Faison talked about, there's 4 aspects. Once you get the data, you got to transform it. You got to transform it in space and time. Sometimes the clocks are not synced between sensors. So you want to make sure that your clocks are synced. Once that is done, you want to transform into the same coordinate system. They need to live in the same coordinate system for us to then approach fusion. If they live in a different world, different coordinate system, then we can't approach the next steps. So that is very important. And Faison talked about the approach that we took. The second step, the most important, data association. We need to figure out which sensor detection belongs to which object, or does it belong to a new object that just entered the sensor perception range. Once we figure out that, we need to do state estimation. That means given an object, its current location, given the detections, can we fuse out of that information to produce a unique estimate of where that object is in the next time step? And then once we do that, we have some object management, get rid of inactive objects, forecast object to the next time step where you're going to get the data, merge similar objects and stuff like that. So, but the key aspect is data association, state estimation. Once you've got this transformation figured out, okay? So let's talk about data association. So at the very basic level, it all comes down to this simple mathematical problem where you have, in this case, I'm showing 2 objects, and you got, 2 objects and bunch of measurements, 5 measurements that you need to associate to these existing objects. Now, when we do this ellipse that you see is multidimensional. So we're tracking, this is a state space approach. So we're tracking position X, position Y direction, velocity in X, velocity in Y, acceleration in X, acceleration in Y, width, length. There's 8 state variables that we're tracking. So this ellipse in reality is an 8-dimensional ellipse, but I'm showing it, let's assume that it's just, we're tracking just position X and position Y, okay? So you got 5 measurements. Now you need to figure out which observation or sensor detection belongs to which object, or does it belong to a new object? And these detections may come from multiple sensors. This just means that I'm looking at one time step, okay? These may come from different sensors. So we're taking the probabilistic data association approach, meaning, first of all, our state is a probability distribution. We have this 8-dimensional probability distribution of each object in the scene, and we get these measurements, and they have uncertainties in them. So it's all probabilistic, okay? First thing we do is we set up a validation region, okay? So this is a parameter that needs to be tuned. We have tuned it, and it basically draws an ellipse around each object and figure out which of the detections fall within. Okay, so for example, for object 1, we found 2 detections that were within this validation region. Then based on how far these detections are from the predicted measurement, that means where the object expected the detection to come, which is the black circle. Obviously, the detections will come not exactly at that point because of the uncertainties and all that other things that go on. So based on the distance, it will assign a weight. So for example, there's 0.358 and 0.658. And based on these weights, that data gets then fed into the state estimator that takes into account that weight. So if the data is farther away, it's going to weigh it less when it fuses it. That means it will matter less. For example, in this object 2, you only have 1 detection, so it has weight of 1. So the weights all have to add to 1, right? Now, these detection may have uncertainties from the sensor. Sensor may also provide that uncertainties, but that will go in the state estimation part. Right now, we're just doing data association. There are two data points that do not fall in validation region of any object that currently exist. So there's two ways. Either you say, okay, this is a new object, both of them are new object, or you say this is false measurements or spurious detections or clutter. We are not in the business of figuring out if this is clutter or not. If the sensor detects it, we consider it and feed it to Fusion. And I'll give you an example. So when I drive in a Tesla and I'm going on a highway and I see a bike behind me and I see on the screen and I see a truck, the bike being identified as a truck, it's fine. It's no big deal. But if there was an 18-wheeler behind me and I see on a screen and it gets identified as a bike, I'd be scared to death. So we take the same safety first principle. If the sensor detects it, we feed it to the Fusion. We are not in the business of figuring out if this is false detection or if this is clutter. If you go in the literature of this data association filter, which came from robotics, there is a lot of talk about clutter, figuring out if this is a clutter. We are not doing that. If the sensor, now there may be uncertainty information attached to that detection. Maybe the sensor tells us that this detection is, very uncertain. That will get accounted for in the state estimation part. But in the data association part, we consider each detection. It's better to over detect than to under detect. So that is the key difference between what we're doing here versus what the literature is on data association out there. So once we do this data association, we then feed it to state estimation. As Stan talked about, this state estimation, Kalman filtering, extended Kalman filtering, uncentered Kalman. This is a well-researched topic. There's a lot of literature. It's well-established area. So we just take these pieces from the literature and we implemented it. And then we keep doing this until we go through all the detections from all the sensors at each time step. Once that is done, we do state estimation, then we go to the next time step and repeat the process again and again. So it's the critical component is this figuring out the data association part. Because when the vehicles are traveling very close to each other, bumper to bumper traffic, data association becomes very complicated, because especially if your one validation region from object one overlaps with the other. So we need to account for that. So once you figure out this, then the data fusion part is all figured out. There's the reference here. This is a very good reference that details this, and then I will go provide a little bit more details later on when I talk about results on the other aspects of the fusion. So let's dive into the results. Okay. So we started with Carla. So Carla, we had these 4 radars, 4 lidars. We just added a Gaussian white noise to the ground truth and expected that this is what the sensors will tell us. Then we go into the fusion. This is 3 vehicles, very simple case. I hope you can see my cursor, and I intentionally created this region where there was no detection. And you can see I'm still retaining my object ID 3. So that goes to the fact that we're using a motion model under the hood. Each object is assigned a motion model, and that motion model keeps the object in the scene for next few seconds. And if it doesn't see any detection about that, it removes it, logs it. But if it sees detection within that certain prediction interval, it will keep the object ID. And this goes to the fact that we are very much interested in the persistence aspect. We want to keep the objects persistent, even if there's outage in the data in the sensor detection. So this was one of the tests we did with this. Obviously, we were just looking at 3 objects. This is constant time resolution. So this is a very simple case. We just started with a very simple scenario. And then we move on to Sumo because we wanted to scale this. Okay, in Sumo, we went with 1 radar and 1 LiDAR. So you can see LiDAR has a 360-degree field of view. Radar has 110 degrees. Obviously has a bigger radial range. We again added a Gaussian noise to mimic what we thought was, the sensor data is going to be looking like. And then we ran this. So now you're going to see on the left is simulated sensor data. You're going to see that a box shaking. That's the Gaussian noise. And on the right, you're going to see the fused. This is what Stan also showed. you can see on the left that when the objects are in both red and blue, you have both red and blue detection, so that meaning both sensors are detecting it. So this all worked fine, okay? Scalable and everything nice, until we went to field data collection. Obviously, real data is very different than simulated data. So I'll just talk about the control setting. So first we went to a parking lot in the city of Colorado Springs. Dan Science led this effort on collecting this data. So we had one LiDAR, 2 radars and 2 LiDARs. We have high accuracy GPS units, as Faizan mentioned. We knew there was this parking lot, it's only us, there's nobody else. So we have these 2 cars. This is us looking at the screens on how the sensors are detecting. On the right, you see that bucket truck, and on the top are the sensors that they're pointing towards the parking lot, and it's detecting these 2 cars. There's nothing else in that parking lot. So it's a controlled setting. Obviously, so when we collected the data, went back home, plotted it, on the left is what it looks like. This is very different from Gaussian white noise. This is not Gaussian white noise. This is something else. So you see a lot of, every sensor lives in its own world. There's some things going on with the LiDAR. We decided LiDAR data was, there's a lot of spurious detections. It was detecting trees, in a wind. And so we just went with the radar detections, and we first transformed it, as you see on the right, and then we fused it. We just look at one vehicle. So you see one vehicle, and you see detections from 2 radars, and we fuse it. Everything works. We figured out that error in position is non-Gaussian. This is the very first observation that we made. The errors are, they're not Gaussian white noise in the reality. Error is different in position, different in object dimension, different in orientation. So there's a lot of things going on with how the uncertainties are there. There's a blind spot close to the sensor. If you go very close to the sensor, you lose the vehicle. So there's that thing going on. So there's different, every field test that we did, we learned something, and we incorporated that in the Fusion engine. Now let's go to the uncontrolled setting. How are we doing on time? Okay, maybe 10 minutes more. Okay.
Yes, you're 10 minutes more, Rimple. Seems like you're good to go.
Okay, great. So this is the last frontier, right? So this is we want to go to the real world, collect data, and then fuse it, okay? So this is data catalog. So we collected the data across multiple days, and there was a lot more data collected, but some days something broke, and so, but the data that we have in this is the best of the best. So, and it comes from 3 different types of sensors: radar, LiDAR, and camera, and GPS. And it's publicly available. It's open source. It's published, and this is the link. And this is the summary, as Faizan also mentioned. You'll see that the key column is the sensors deployed column. You'll see every day we had different quantity of sensors and different time resolution. This tells you that when we go there, sometimes something breaks and we adjust and we do different runs. So that's why there's differences in the time resolution and the number of sensors and the types of sensors deployed in each date. This was not intentional. But the best data we have is from November 22nd date. We have 3 different types of sensors which we wanted to capture. They're all at 10 hertz, which is great because we wanted this high resolution data. So this is out there. So I'm going to focus on just that moving forward. So this is the intersection that we collected the data from. So you'll see this intersection in the city of Colorado Springs. There's a statue in the middle. There's an IPC trailer. That's where we parked our trailer, where the sensors are going to be hoisted. And there's a school on the right that produces a lot of pedestrians. So this is, we selected this intersection. It's very complex test bed because we wanted things to break. We have been living in this simulated environment and everything was nice and happy. We wanted our Fusion engine to break at multiple places. And so we went to the complex environment here. Obviously, statue creates a blind spot. The sensor loses the vehicles that are behind it. So, and their school creates a lot of pedestrians. So there's that. So this is a very complex test bed, but it's good test bed to test this, the Fusion engine, make it robust so it works in the real, in the field. So this is during the test, we have this IPC trailer. There's obviously 2 poles here, and each pole has a radar and lidar and camera. And this is the another picture on the right. And so once you transform it, as Faison already talked about, this is what it looks like. You see the statue in the middle. There's nothing there. There's school, there's IPC trailer. You have 5 different sensors. Obviously, each sensor has its own range. So let's look at each of them. Okay, first let's look at the radar. Okay, these are EVO radars. They're pointed in different directions. You can see 110 degrees spatial angular range. There's some detections outside that range. That's fine. That's typical. And so these are 2 radars. Obviously, if you want to point them in the direction of the approach. And these are the lidars, obviously 360 degrees. You're getting a lot of detections outside that 50-meter radius range, or OEM provided range. Now, there's a lot of predictions there. As Faison mentioned, Ouster OS1 lidar, they also provide predictions. That means under the hood, they have a model like we have, and they provide the prediction estimates as well. But in the Fusion engine, we don't consider that. We only consider the raw detections. Because we don't know how they're predicting, how trustworthy they are. So we only look at the raw detections that came from the point cloud data, not from a different model that they have it under the hood. So we have this, and then we have the camera. Now there's some issues with the camera. You see a little bit of warping at the edges. That's typical. So we decided that we only will take into account that data that falls into this arc. So once you get this data, apply exclusion zones. Obviously, you don't want to track vehicles on top of the buildings away from the roadway. So you exclude the data because you don't want to. It's not important. So you only focus on roadway, and this is the data that now is going to go into the Fusion engine. Okay, so there's 4 key components of Fusion engine. Okay, this is very important. So first is motion model. As I talked about, there's a motion model for each object that gets created. That motion model we're using white noise constant acceleration model. As I mentioned, it tracks 8 things about each object. And there's uncertainties associated with it, and it's probabilistic. Okay, there's different models. We have tried different models, and in the software that I've shown in the bottom, there's different options that people can choose and try to play around with. There's the measurement model. How does your state relates to the observation that a sensor provides? So radar, we are assuming that it provides these 6 variables, so it doesn't provide acceleration. The LiDAR, we are assuming the same thing. The camera, we only have position and position Y. So this goes back to my discussion about each sensor captures different things and different uncertainties. So there's that part. State estimation, we're using Kalman filter because it's linear motion model, linear observation model, but nonlinear filters are also implemented and available in that software. So people can play around with different nonlinear motion models and nonlinear observation models. And then this sensor fusion. So there's parameters. So first is the gray threshold. So remember the elliptical region I talked about, you need to tell the sensor fusion how big you want that region. Okay, we have some suggestions in the code to start, but people can play around with that. There's predicted lifespan, how long you want to keep tracking the object without any detections. Okay, so in this case, we have 2 seconds, but we can play with different. Obviously, the longer it is, the longer the object is going to stay in the scene. It also depends on what the time resolution of your sensors is. The association probability and the merge threshold are another parameters that controls aspects of data association. So this is the final fusion of that data that I showed you from November 22nd. So let me just step back and summarize what's going on. This is open source multi-sensor data fusion software fusing data that's available open source, collected in the field from 3 different types of sensors, from 3 different OEMs, in real time, stop and go vehicles, fast moving vehicles in this complex signalized intersection. And we have done, this is just 2-minute snippet, but we have done this for all the data that we have. And so this is where we are. Okay, we have performed fusion on different types of sensors with different characteristics. And so I'm just gonna keep it here. You can see there's some persistence going on. It's very far from the Gaussian noise that we looked in the simulated environment, but we were able to overcome those challenges and produce this sensor fusion that is able to handle this. So let me conclude what do we have so far? We have open source sensor data collected from field. We have open source fusion software that can run on that data. There's few things that we're working on or we're looking into the future. First aspect is real-time deployment. Right now, we collect the data, we come home, we fuse it, but can we do that in real time at the edge? So this piece is important. We're going to work on that. Control aspect. So far we have talked about the perception aspect. The control aspect is going to come as well, and then including additional data sources like V2X. This is very important. This is in pipeline as well. So with that, I'll just stop here and send it back to you, Stan.
Thank you, Rimple. Thank you for bringing us home there. I know that was highly technical, but it provides a good ending point of where we're at today and how we're moving that forward. I'll open it now. I know there was one thing in the chat, Matt, I responded to. If you have any questions, please put it in the chat or unmute your mic and we can take them at this time. While we're doing that, I will answer a couple of top-level questions. First of all, if you're interested in this material, much of it has been published. Here's a slide that has a good majority of those that are currently published or in the publication chain. We have a pretty strict publishing protocol here at NREL. So people ask if this webinar will be available for later use and the slides. The answer is a conditional yes. We have to take this and send it to our publications branch to make sure that it meets their standards. After this, I was going to bring up our question slide. If you have any follow-up questions for any of the speakers, I listed all the speakers here and their email address. Please do not hesitate to ask. With that, I'm going to go back to our chat. I see there's a couple of comments in there. GitHub doesn't seem to work. Eric wrote something in there.
Eric, I'm looking into that. I'll fix it.
That doesn't, I didn't type that in.
Okay.
So I have no idea what's going on there at all.
Okay.
We'll double check to make sure the links work. Anyone else with any remaining questions? If not, we'll bring this to a close. I want to stop sharing my screen. Again, like to thank all of our speakers. This information has been aggregated, the majority of it over the length of the USDOT SMART grant. We are involved in half a dozen other efforts that are smaller in nature that pushes the IPC framework forward in various aspects. We do have an association with the UCLA Center of Excellence for New Mobility and Automated Vehicles that will continue some of this work forward. Any last word from any of our speakers? Right. Again, thank you to USDOT SMART grant, to the City of Colorado Springs for all the support through all of this. We feel we're in a very good position to move this forward generically as a overall framework, making all of our work available in the open source domain. Thank you, everybody. And from here, signing off.